I would like to derive the wave equation for you since we're going to need it in electromagnetic theory when we solve the Maxwell equations in free space. And to do that, I set up a little pulse here where the function at x equals 0 is a maximum. And I write that as f of 0 is a peak. The exact shape of the pulse, I really don't care. I just want to point out that the 0 position here, f of 0, is a peak. And how does that peak get shifted to the right? Well, to get shifted to the right, I need to change the argument to x minus d. Why is that? Well, if this becomes a new function, h of x, then when I put in x equal to d, h of d will be equal to this function f of the argument d minus d, which is f of 0, bingo, that is peak, which means that the peak has been shifted to the right. So remember that rule, shift to the right, use the minus sign. And in a second, we're going to let that d equal v times t, and then we're trucking along down to the right. You probably have seen something like this before with trigonometry, where if you have the cosine, the green one, and if you shift it pi over 2 to the right, then you get the sine. So the sine of x is equal to the cosine shifted to the right. Remember, the shift to the right means the minus sign. So x minus pi over 2. Since the arguments inside the cosine can be flipped in sign and still get the same result, since cosine is an even function, cosine of theta is equal to the cosine of minus theta, you can flip this pi over 2 minus x, and when you do that, if you have an angle x, pi over 2 minus x is the complement, and you know that the sine of an angle is equal to the cosine of its complement. Well, let's go ahead and let that d equal v times t, and then we have the wave traveling to the right, and we're in search of a differential equation for which this is the general solution. So when we do that, we start taking derivatives. Well, what's the derivative of the function with respect to x? That psi is often used for waves, so I'm using that psi there as a wave function. And here I take the derivative with respect to x using chain rule, df du, and then du dx, df du, I don't know what that is, and I don't care. Du dx is 1, and I get df du. When I do the derivative with respect to time, I get the df du times du dt. Du dt is minus v, and I have the f du times the minus v. I divide by minus v on this bottom one so that I can have the same right-hand sides, and I can set these equal. So the partial of psi with respect to x is equal to 1 over v with the minus sign there, times the partial of psi with respect to t. That's the wave equation for waves, unfortunately, only traveling to the right. Because if v becomes minus v and I want to go to the left, I then get a different differential equation, and that's not allowed. We can't have that. There is nothing different about going to the right or to the left intrinsically in terms of traveling wave. In fact, you can turn around and call the left one the x and the right one the minus x. So we can't have two differential equations. We have to have the same one. So it's time to crank out more derivatives. And here is the secret here, the intuition. To get the v to be independent of the sign, we want v squared. So that would mean taking the second derivative with respect to t, because that pulls in another minus v somewhere in a chain rule. So minus v times minus v give you plus v squared. But if I do that, I'll have the second derivative of the f with respect to u. So I need to take the second derivative of psi with respect to x so that I can set up the equality. So that's what we're going to do here. That's the inspiration. The derivative of psi with respect to x again means that we'll have the second derivative of f with respect to u times the chain rule factor, which is 1. Du dx is 1. And that's the second derivative of f with respect to u. I don't care what this is because it's a general function which can be any shape that's traveling to the right. Then when or we're going to see here also to the left. And here, when I take the derivative with respect to time, again, I simply insert this into where I'm going to take my derivative of all this stuff. The v is constant, comes out with the minus v. And then the second derivative with respect to u, with the chain rule, the du dt gives me another minus v. Minus v times minus v is plus v squared. And now I'm in good shape. When I divide by v squared to get the right-hand side to be the same, I can set these equal. The second derivative of psi with respect to x is 1 over v squared, a second derivative of psi with respect to t. And why does the v go here? Very easy to remember. Remember, think of this as distance equals velocity times time. Distance is velocity times time for the units to come out right. So if I square distance, I have to have the velocity squared, and I'll have a square here. Unit-wise, these things are squared. They're really second derivatives, but the effect is when you have the units, you're going to have here 1 over the meter squared because of that, and then you want to have the dimensions come out correctly. The psi dimension, will, whatever that is, if it's pressure or something, just the same on both sides. We don't have to worry about that. But down here, different things are going on. So you want to make sure that you have the units come out right in the denominator. So just think x equals v times t, distance, velocity times time, and you always get the velocity in the right place. That's the wave equation, and it doesn't matter if you're going right or left, minus v or plus v, you have the v squared. And a second order differential equation has 2 solutions, independent solutions, and here they are. A function I call f, which is traveling to the right, and I'm using g here to represent the function that travels to the left. But this psi can be then a combination of these two. For 3 dimensions, we add in the other dimensions. We have the second derivatives with respect to y and z. We add them up together. And when we use our del operator, we can write that in shorthand notation because del dot del is going to be the second derivative summed up. And that's also the Laplacian, which we talked about earlier. This is a little bit of a review here. And this is a very beautiful and compact way to write the wave equation in 3 spatial dimensions.